but yeah, this is started over 10 years ago now. And it starts with sweetgrass garden. So Dr. George Taylor, former cardiologist, and there he is on the left with some EnSoil treated basil. It's really popping. So he, working in the medical fields, Dr. Taylor started to see a connection between health disparities and also, or with, health disparities and related to nutrition. So he purchased some land on Johns Island, South Carolina, and the goal was to grow nutrient-dense food without chemicals that could feed locals in need. And so he called it not Sweetgrass Garden, established as a nonprofit. And when we began soil testing, Dr. Taylor learned that the land needed regeneration. So him and other members of our team went down a path and found Chlorella vulgaris, or rediscovered Chlorella vulgaris, because this living green algae has been used since the late 1970s. There's research, but we're sure it's been used as a replacement for fertilizer for many years. So after using the algae on the soil and seeing the benefits, seeing the improvement in the soil health and plant productivity, Dr. Taylor asked himself the question that started Enlightened Soil Corp, which is, why is Chlorella vulgaris not commercially available yet? And the answer was threefold. One, algae wasn't, all these biologicals were coming out, but algae wasn't in the initial wave at the moment. Fertilizers were still kind of affordable. And the biggest one is that nobody had figured out how to bottle and ship these living algae cells yet. So between 2018 and 2020, Dr. Taylor and his team set to develop a grow process that could bottle and ship the live algae cells and accomplish that. So Enlightened Soil Corp was formed shortly after in October 2020. And this is a process that we now have patented, which is exciting. So, and in the meantime, the team had been working hard with local growers in South Carolina, collect data and validate the observations that they were seeing at Sweetgrass. And then by 2021, Enlightened Soil received a SARE grant based on Iron Horse Farm, which is right near Sweetgrass, to answer the following question: does reduction of nitrate inputs in pasture land treated with Chlorella vulgaris result in cost savings and healthier soil and grass? So here's some before and after pictures. The number 1 ranked pasture was treated with algae alone, and the number 2 ranked pasture was treated with algae and 25% of the usual NPK input. And now Iron Horse, and this was in 2021, now Iron Horse doesn't use fertilizer at all, and it's no coincidence that the pond nearby no longer has algal blooms. So this trial, it's the first big one. We've had a lot since then, and it's at the heart of our mission, which is to help the world transition away from chemically dependent agriculture. And we want to make it clear, EnSoil algae is not a silver bullet, but it is a very reliable tool in the world's toolbox for helping with this transition. Chlorella vulgaris is just one microorganism that has a role to play. And also, to point out, you can tell we started the company during COVID, so you can see the social distancing going on in that photo.
Great, thanks, Yaz. So if anyone has any questions about this story, just make note of those and we'll answer those towards the middle of the webinar. So we're now going to move into the mechanisms of how this algae works. So as Yazzie said, the strain of algae that we work with is called Chlorella vulgaris. This is a freshwater microgreen algae, and it works as a powerful biostimulant, which means it's encouraging natural processes of nutrient cycling and soil microbial activity to stimulate plant growth. So there's really 4 mechanisms that we have collected data on through working with growers across the country. We currently have EnSoil on 45 different states. I believe that is the up-to-date number. And there are 4 things that we have collected data on. So I'll go through these briefly right now, then show you an infographic that explains it a little bit more in a visual way. And then Dr. Taylor will talk more about the mechanisms of the biostimulant. So the first way is that the algae cells stimulate and grow microbial populations and diversity. These are microbes such as bacteria, fungi, protozoa, nematodes that are found in the soil. They're little organisms. Second, the EnSoil algae increases the plant nutrient uptake and stimulates the overall plant growth. So it's really an accelerator, it's a catalyst. Third, the EnSoil algae enhances chlorophyll, which is that green pigment that you see in plants, and it improves their photosynthetic capacity, so their ability to take in sunlight and produce sugars and store energy. And then finally, the algae increases the plant tolerance to stress. So stress could be things like drought or high salinity in the soil. And it also increases the soil water retention capacity. And this really means that you're able to hold moisture in your soil. And the reason that this is happening is because of those soil microbes. They're like construction workers, and they are building structures where we can have porosity or little spaces in the soil where we can hold water. So let's look at an infographic on how this works. This is comparing EnSoil with a synthetic NPK fertilizer. For those of you that maybe are not familiar with this term, this is your conventional agriculture fertilizer that is adding synthetic nutrients such as nitrogen into the soil. And as Yazzie said, EnSoil is not a silver bullet. We are not a one-size-fits-all solution to an agriculture problem. We are one of many solutions that can help repair land. And this is just a comparison between what a lot of conventional growers are using. So we'll start in the bottom right-hand corner. And when you apply EnSoil, you apply on the foliage and on the roots. And so the cells go into the ground, into the soil, and they stimulate the growth of your microbe community. So you get an increase in population, you get an increase in diversity of species of microbes, which is really important. And those microbes become active. Second, as we move up the right side, the bacteria, these soil microbes, are able to fix or convert nitrogen that is in our atmosphere, in the air that we're breathing and the air that's all around us, into usable forms for plants. So nitrogen is something that is, proteins are made up of nitrogen. So plants need nitrogen to grow, and bacteria help them access this nitrogen. So the plants are able to take up those nutrients through their roots and utilize them. Third, when EnSoil is applied, the chlorophyll, like I said, that's the green pigment, is enhanced and the plant photosynthesizes more efficiently. We've had a lot of growers who say, you know, after they spray their algae on their fields, they can actually see that it's a little bit greener or a little bit brighter, and that's that chlorophyll. So this allows the plant to release more carbon into the soil. I know sort of a buzzword term right now is carbon sequestration. For those of you that don't know what that means storing carbon into the ground. So taking carbon dioxide out of the atmosphere and bringing it into the soil. And this is something that EnSoil algae helps with a lot because the plants are able to draw down those sugars into the soil through their roots and store the carbon there as opposed to in the atmosphere. And then fourth, at the top of the right-hand side, EnSoil algae increases that plant's tolerance to stress. And like I said before, this is really the work of the soil microbes. They are able to have the water retention capacity increase. They're able to improve infiltration. So areas where folks have a lot of drought, I know we have maybe a couple of folks from Arizona here tonight. And EnSoil is a really great way to try to retain more moisture in the soil. And I think Dr. Taylor is going to talk a little bit about how the algae actually works on plant tolerance. But first, let's talk about how this is different from a synthetic fertilizer. So on the left-hand side, I'm starting in the top left. And when we apply a synthetic NPK fertilizer, the synthetic nutrients are being added to the system. And this is a really key difference between EnSoil and a fertilizer. is that with EnSoil, we're not adding any nutrients. We're using what already exists, the nitrogen and the carbon that's already around us in our environment, and cycling that with the use of these microbes. But using a fertilizer, you're adding additional nutrients. So this nitrogen is inaccessible to plants without the strong soil microbe community to fix it. And what happens when we have this loose nitrogen in the soil, now I'm on number 2, and it's not stored in plants or bacteria, it's really likely to contaminate local water systems. And so you may have heard the term runoff. And if you've heard runoff with, related to fertilizer, what's happening is that nitrogen is not being stored, and therefore it's going through the soil and into the waters. And then we have these synthetic nutrients in our water, which can cause a lot of issues contamination wise. Some of that nitrogen will also move back into the atmosphere. Excuse me. Number 3 on the left-hand side. So when we have excess soil nitrogen, just meaning there's too much and it's not stored somewhere, it creates an unlivable habitat for these microbes. So some of the microbes will die, their habitat will not be as alive and healthy for them, and they won't be able to function in the same way that they're meant to in this living soil organism. So finally, number 4, once all of the plant nutrients are used up or they've moved out of the soil is now dead, and the plant needs new nutrients to grow, which requires this dependency. We talk about chemical dependency, requires a dependency on synthetic fertilizer, which requires more money and more time to add those additional nutrients back. Whereas with EnSoil, we are able to use the local ecosystem literally right there at the plant to cycle these nutrients and to increase the health of the soil. So I'm going to turn it over to Dr. Taylor now, and he will share his lovely wisdom with you all.
Camille, why don't we leave that slide on the screen?
Sure.
I'm going to start with kind of a philosophical comment. This is all about different organisms communicating with each other. I mean, why should algae communicate with soil bacteria? Why should algae communicate with plants? I mean, they work to directly stimulate plant growth. By the way, we don't use the word accelerant. The EPA doesn't like it. But how can different life forms communicate with each other? And I think it's because we all started out in the same place. When the world was brand new and life was first forming, single cell organisms, a lot of it cyanobacteria, and then algae. A lot of them that were successful as life forms branched out and developed, the successful systems were kept. So in the plant kingdom, things like auxins, which stimulate root growth, things like cytokinins and gibberellins, they were being produced, they were developed and being produced by these very early life forms. Because they worked, they continued to be used by higher plants, and they were used by bacteria. So it turns out that the signaling molecules that stimulate plant growth and that stimulate bacterial activity are shared by higher plants, by bacteria, by algae. One way the algae works is it gets into the soil and it stimulates bacteria to do their job, fix nitrogen, and dissolve phosphorus, for one thing. We think that, well, it's assumed that the algae are releasing stimulating organisms, signaling compounds that directly stimulate the bacteria to do their job and to grow. We see an increase in organic matter, which is basically made up of soil bacteria and other microbials. One teaspoon of soil, healthy soil, contains as many as 10 billion, right? 10 billion bacteria in the neighborhood of the roots. And it's these bacteria that basically are responsible for nitrogen fixation. When I was taking biology in high school, I heard the term nitrogen fixation. I was taught that that was something plants did, but it turns out that the real engine for nitrogen fixation is soil bacteria. Legumes, of course, are planted to increase nitrogen in the soil, right? But it turns out that the nodules in the roots of legumes are packed with bacteria, and it's those root nodule bacteria that are fixing the nitrogen. We've been doing a lot of soil testing with it over the years, and using fancy measures of bacterial activity. The test that's most commonly used is called Haney testing, developed by Rick Haney when he was at the USDA. But one of the measures is soil respiration. They take soil, they dry it, and then they re-wet it and measure the amount of carbon dioxide that's released. The bacteria breathe in O2, they breathe out carbon dioxide. And this measure of exhaled CO2 by the bacteria is an index of the size of the bacterial community. We also have done a lot of direct testing using a method called phospholipid fatty acids. Those are compounds that are present in the walls of bacteria. And PLFA testing has shown directly measures this increase in the microbial, not only quantity, but also diversity of microbials in the soil. So that's kind of how the algae works. It stimulates natural soil processes. There are a lot of other biostimulants, and they do the same thing, but they do not have live cells. To back up a bit, there was a lot of university research being done in this area as far back as the early 1970s. And when they did the work, they actually would harvest algae locally that they grew in a tub, and they would spray that directly on the field as soon as they harvested it. And they showed an increases in growth and yield, and an increase in soil health. In fact, a lot of these studies actually took the algae, spun it down and threw away the water it was growing in, added new water, and then sprayed it on the fields, and showed that these favorable effects. So the live cells were considered important. But it turned out a business never really developed around this, because when you put a green plant in the dark, when you put it in a bottle like these and stick it in the fridge or put it in a dark root cellar with no light, the green plant dies. And that's the case with the green algae. We found that if we put untreated algae in the dark, the cell counts fall by more than 50% in 3 to 4 days. The algae just dies off. So other biostimulants have taken a different approach. The more sophisticated companies actually harvest the algae, break up the algae cells, and extract the biostimulant compounds. So a lot of European companies do this, and they will sell a preparation of auxins, or sell a preparation of cytokinins, or a preparation of gibberellins, a preparation of salicylic acid. Pretty sophisticated biochemistry being done there. The simpler way to do it, and there are a number of American companies that do this, is just to harvest the algae, throw away the algae cells, and use the juice, the water that the algae grows in, so-called growth medium. And the algae, as they're growing, are releasing these same biostimulants. So the growth medium contains the biostimulants, and those can be sprayed on for use as biostimulants as well. The problem is that you spray them on, and it's one shot and they're gone. A lot of these companies recommend weekly application of the cell-free biostimulants. Biostimulants with live cells, we think that the live cells continue to produce these compounds. And so it's like a long-acting medicine. The cells go down and they keep producing the active compounds. There's pretty general agreement that having the live cells is useful. In fact, some of the biostimulant companies, in addition to selling the extracted compounds, will also sell a farmer a system for growing algae so that they can grow the algae themselves and then put it on the field as soon as they harvest it. That's kind of a losing proposition because it's not that easy to grow. You know, we grow the algae in 60-gallon test tubes, big tanks that are like 7 or 8 feet tall, containing 60 gallons, or we have some tanks that are 200, 240 gallons. It's done with grow lights. It's a monoculture of Chlorella vulgaris, but we have developed a process when growing the algae that allows the cells to continue to live in the dark. If we have a breakthrough, that's it. We've figured out how to preserve live cells for use as a biostimulant. So how do you do that? Well, we're getting back to basic biology here again. Half of life is what is known as heterotrophic. You and I are heterotrophs. Bacteria are heterotrophic. We eat other organic material. We eat food that we don't make. The plant world, including algae, are autotrophic. They make their own food. Algae plus light plus water plus CO2. These are the ingredients for photosynthesis, by the way, produce more algae in the plus sugar, glucose, plus the only byproduct of manufacture, which is oxygen. Plants breathe in CO2, they release oxygen. The bacteria are no different. We have so the breakthrough that for us was the discovery of a process during growing, which changes the algae behavior so that the algae, in addition to being autotrophic when there is light, becomes heterotrophic in the dark, meaning that the algae in the dark are able to eat other organic material. They act like bacteria. You know, they're able to eat any organic material that's sitting there in the tank with them. As a result, the algae can continue to divide and prosper in the dark. And what we've found is that we have, with this process, we have algae that we've stored for 18 months. And pull it out after 18 months in the dark, the cell counts are still up. We look at it under the microscope, it still looks like green, round, little green cell algae. We plate it out on growth medium and it starts to grow. So the discovery of a heterotrophic growth mechanism for the chlorella is the secret to having a live cell biostimulant business. It's as simple as that. Camille touched on a lot of the things that the algae does, and I'll tell you, one of the problems with this is that it's kind of a too good to be true story. You know, when they come to you and say it does this, and oh, by the way, it does this, and oh, by the way, it does that. After a while, you've got to start thinking, what's going on here? You know, and that tends to be one of the problems when talking about chlorella, live Chlorella vulgaris. Oh, by the way, there are indicators that the Chinese were using this 2,000 years ago on rice, the biostimulant approach. It's not brand new, and the university research, there's good university research on mechanisms going back to the 1970s. But what is it? What can it do? Okay, number one, it does stimulate microbial activity in soil. The number of bacteria increase, the number of fungi increase. and the diversity increases. Putting all that together, there's an increase in organic matter. Number two, sprayed on foliage. There is a direct stimulation effect. And a lot of people feel that the chlorophyll increase probably has to do with that foliar spray part of it. Number three, it increases resistance to what they call abiotic stress, which is drought or salt and irrigation water. Other abiotic stress might be cold, might be heat, but drought's the big thing. What happens with drought biochemically? What happens with drought is the buildup of oxidative compounds like peroxide within the plant, and those compounds injure plant tissue. There are great university studies showing that with biostimulation, and certainly live algae, Chlorella vulgaris stimulation, the plants, by the way, make enzymes to detoxify these oxidative compounds. They make peroxidases. They make superoxide dismutase. I love saying that term just because it sounds so cool. But basically, one of the compounds is O2 with a negative charge, the superoxide radical. And that superoxide dismutase breaks that down, turning it back into just plain oxygen. But plants make these compounds to combat the oxidative stresses. With algae, the level of those enzymes is higher in the plants. And that is why the plants are more drought tolerant. People doing real dry land farming have been having success with the algae for that reason. And then a final thing worth mentioning is this whole business of runoff of nitrates. NPK, synthetic chemical fertilizer, is soluble. You mix it up, it goes into solution. You can shine light through it. And it dissolves in water, and wherever the water goes, it goes. It turns out that plants only use about 30% of the nitrogen that's applied as synthetic fertilizer. Okay, the rest of it winds up washing away into groundwater. If you live in Iowa, that groundwater winds up eventually in the Mississippi River, and that eventually winds up in the Gulf of Mexico. And the dissolved nutrients, the nitrates and the phosphates too, basically stimulate wild algae growth in freshwater as well as the Gulf. It was interesting that when we were first doing studies at Iron Horse Farm, one of the fields we were working on has a big pond down at the end of the field. The ranch owner called us one day and said, "What's going on with this algae? You're killing my pond. I've got algae bloom." And we went there, and sure enough, there was scum. There was algae bloom on the surface of the pond. But it was over on a section of the pond that was being treated with NPK. The end of the pond that was being treated with the algae was fine. We pulled off the stuff and tested it and looked at it. And it turns out that the wild algae bloom was not Chlorella vulgaris. It was cyanobacteria, so-called blue-green algae, which is totally different. And if you look at algae bloom everywhere, most of it is cyanobacteria, another very, very common soil microbial. It turns out that using chlorella is a solution to this wild algae bloom. Why? Because we're using it to replace the nitrogen and the phosphorus that goes into solution and gets into the rivers. Well, if you look at a bottle of the chlorella, it's been sitting for a while, it looks like water. And at the bottom, you see a rim of green, and that's the algae that settled to the bottom. It's like orange juice. Doesn't go into solution, it's particulate, and it settles down in the bottom of the container. About 4 or 5 gentle shakes, and it's dispersed and is green again. The whole thing is light green. It turns out that these algae particle cells, which don't dissolve in water, don't fight their way through soil to get to groundwater. They get maybe an inch, a half an inch past the surface, but they don't go any farther than that. They're not able to shoulder their way through sand or clay particles to get deep, number one. It turns out that the soil has got a net negative charge, and algae have a positive charge. So as the algae tries to move through, bang, they get soil bound just because of magnetism. And finally, we don't see algae bloom because are the algae getting through to groundwater because not that much is put on. The dose of algae getting on a field is 50,000 cells per 1 square foot when used as directed. Then that sounds like a lot, doesn't it? But wait a second. 1 teaspoon of soil has 10 billion bacteria. So 50,000 cells, how can it work? It works because the signaling molecules that are produced work in tiny, tiny concentrations, parts per billion. It's tiny, tiny amounts of oxidants and cytokinins and gibberellins that actually are broadcast by the algae cells and do the work. So for these reasons, the algae doesn't penetrate, doesn't get into groundwater, cannot cause algae bloom. And it's frankly switching from chemical fertilizers to this approach, there's going to be less algae bloom. There are a lot of farmers who get into trouble with their neighbors because the lakes that abut their farm are being contaminated with algae bloom. It's a big problem. It's a huge problem in Florida, by the way. Big enough problem in Florida that they have nitrate blackout periods during the year where you're not allowed to use synthetic chemical fertilizer during certain times of the year where algae bloom is a big deal. This is a solution to that. Maybe that's enough science.
Or do you want to take some questions?
Let me say one other thing about this, though. Let me talk about business.
Sure.
Let me talk about the farming business for a minute. Frankly, I got into this because I just love the science part, but the business aspect is interesting too. When we present, most farmers that we present this to want to try it, but the usual response is, look, I got to make sure it works on my soil before I use it whole hog. So my wife's cousin has 2,000 acres of corn and beans in central Illinois, and he's put it on his corn and beans and on 10 acres of corn and beans, not 2,000. It's worked. Next year, he's going to put it on a bigger area. Third year, he's probably going to use it on everything. But the big thing for farmers is ROI, return on investment. Some farmers are chasing yield, but I think the smart business move is to chase return on investment. Chasing yield, you might continue to use your full complement of NPK and add the algae to it. Some people are doing that and are getting great results. But where the real savings, the real money savings come is in reducing the amount of NPK that you use and putting the algae in. The algae is a lot cheaper than the synthetic chemical fertilizer. And we found that with most crops, you can maintain yield. You can maintain yield and growth by reducing the NPK by 75% or more and putting in the 50,000 algae cells per square foot. And that results in a huge reduction in the cost of inputs, in nutrient inputs. So that's what people are doing is they'll use it the first year just to be sure it works. When they see that it works, they use it another year, and they start dialing down the amount of NPK they're using. And over a period of time on their ground, they figure out how much NPK they can afford to reduce. And it's kind of crop specific. We've been doing studies with Clemson Ag. Clemson University Agriculture, and when it's used in peppers, reducing the NPK by 70–80% is great with the algae. When using sweet potatoes, algae alone is fine. There was nothing gained by having any NPK in the soil. The algae worked as well as anything else. So it's kind of crop specific too. And one final note on the business. I don't know, we probably had more than 200 farmers use this, as Camille said, in 45 states, including Hawaii, by the way. I would guess that close to 100%. I cannot remember a farmer who's used this who did not use it or reorder it for the second year. That's the bottom line. It works. I'll tell you, when I first started with this, and I look at this this liter of almost clear liquid, kind of light green, or I knew there was a little skim of algae cells on the bottom before I shook it up. And by the way, a liter of it treats 4.5 acres. You look at how many acres you have. You add the appropriate amount of algae for that number of acres, and then fill up your sprayer and pull it behind your tractor. People are using it in pivots with great success. I thought, man, how can this stuff work? But we've had enough university trials and enough real world trials, farmers using it, that I'm a convert. It does work. And as I say, pretty much everyone who has tried it wants to continue to work with it. That's the bottom line on this whole thing.